going to start looking at end behavior. Now, guys, are you okay with these shapes of polynomial functions? Are you okay with shapes? Okay. So here's what we want to start looking at, guys. Determine end behavior of these. Now, I'm going to put a star by this one, or check mark by this one and this one. This one here, these are things that we can use our chart for in terms of what it looks like. But, guys, they say up there, what's the end behavior of each function as x approaches either positive infinity or negative infinity? And, guys, the first thing I'm going to ask you, what degree is this function over here? It's a third degree function. Furthermore, it's a polynomial function, right? Is your leading coefficient out here positive or negative? So for a third degree function, we kind of know the answer here. If you go up your third degree function, positive coefficient, as x goes to the right, as x goes really far to the right, where's your graph going? Positive infinity, right? So I'm going to write down this for this situation. We would say as x approaches positive infinity, kids.
Y approaches positive infinity.
You can say y approaches a positive infinity, and they're probably going to use what notation instead of y, according to the way it's written.
F of x.
Yep, so if I can say f of x is going to approach infinity. Can you guys read that up there okay? All right, and then how about as x approaches negative infinity, kids? Yep, f of x is going to negative infinity. It's moving down, so the graph is kind of like this. Okay, so f of x is going to approach negative infinity. So I want you guys to try, I want you to try this one right over here on the far right. See what you come up with, okay? This one on the right, first of all, guys, what'd you put down as x approaches infinity? Where's f of x going?
Positive.
Yep. F of x approaches positive infinity. What about as x approaches negative infinity? Or way to the left, where's the graph going?
Positive.
Yeah, it's even. It's an even degree, so leading coefficient, positive, going to be like this, isn't it?
Yeah.
Can you remember those this, and this? Think. Look like the Tin Man when I do that stuff, but I think it's helpful. All right, well, let's talk about this graph right here, guys. What do you know about this function right here? First of all, is it a polynomial, or is it something else?
It is. Well, it's
So it's a polynomial or a
It's a
polynomial, it's a
rational
rational function, right? Okay. Now we gotta be careful on this here, because when we graph this right here, you know, what's gonna happen? Would anything cancel out of this, kids? So no matter what you put in for x, kids, it's just gonna be what value? This is like saying the function f of x equal 2, and isn't that just a horizontal line at 2? So as x gets really, really, really big, it's still equal to what? So I might right here, as x approaches positive infinity here, what's f of x going to approach in this one? 2. And as x approaches negative infinity, f of x is going to approach what again, kids? Okay, now if you're ever not sure right here, where might be a good place? Yeah, you're not sure.
Desmos.
Look at decimals. Now, guys, I think my numbering system on examples got screwed up. Okay, when I wrote these notes, I think I skipped an example 3. Is that right?
Yeah.
We're not missing anything. I just counted the wrong way. Okay. All right.
Example 2 is next.
All right. So on this page, are we good with notes on this page right now, kids? All good?
Yes, sir.
All right. Let's move to the next page here. Here we go. determine the minimum degree of a function. Let's see, and the leading coefficient. Let's see how good you guys are. How many bumps does this graph have over here?
3,
So it must be at least a what?
4.
Has to be at least a 4th degree, right? And by looking at that function right there, leading coefficient can be positive or negative.
Positive.
I'm gonna write positive k here, alright? You guys do the next two. Tell me what degree, at least, at the very least, what degree, and then, and if you look at the end behaviors of them, guys, you gotta know that this degree on this next one's gotta be what kind, odd or even. The middle one's gotta be odd, because they go in different directions. So talk to me, what's your minimum degree here?
5th.
Leading coefficient, positive or negative, based on your end behaviors here.
Positive.
Yep.
Has to be odd.
How about this?
4.
At least a 4th with what? So you're telling me that this graph and this graph have similarities, is that what you're telling me?
The same graph, just in
Pretty much, it's just different valid points, different parameters to it, okay? So if I ask you, hey, here's a graph, can you tell me the minimum degree? Alright, secondly, can you tell me if the leading coefficient based on some of those polynomial shapes that we have would determine if that coefficient's positive or negative? Could you do that? Okay. Alright, it says graph the following functions in what, kids? Desmos to determine if a function is odd or even. Let's just write this down. If a function is odd graphically, it must be symmetric about the, anybody remember? Yep, it means it's symmetric about the origin. Must pass through the origin, and then if you make half a turn, it's the same exact graph, okay? Everybody recall the rules for being an even function? Symmetric about the y-axis. The y-axis is your divide line. Okay? So if it's odd, it's symmetric about the origin. If it's even, it's going to be symmetric about the y-axis. So, let's jump into Desmos here. What's the first graph I'm going to throw in here, kids?
X is equal to x squared minus 2.
And when I type in my x squared minus 2, here we go. Here's my graph. Now guys, what degree is this function? Second degree, so we know it can't be odd right off the bat, right? So I have a question for you. Is it symmetric about the y-axis? Yeah, it's even, right? Okay, so you guys take a minute, graph those in Desmos, or if you want to get with a partner and graph together. This one here is going to be even because it was what? Symmetric about the, okay, so we've got symmetry to the, yep, y-axis. Squeeze that in. And we've got symmetry with the y-axis, alright? You guys try B and C on your own with graphing and see what you get. Let me ask this question, before you even graph them, what can't the last two be?
Even.
They can't be even, so you're checking to see if they're what? Odd, because the degrees of both of them are odd, aren't they?
So can they be neither?
It can be neither, yep. And in fact, I'll tell you one of those is a neither. What's the third one? X to the third, or X, second one, X to the third plus. Hey guys, take a look up here at your second one. notice? Pass through the origin.
Yeah.
If I made half a turn with this, would it be the same exact graph? So therefore, it's symmetric about the origin. So what type of graph must this be?
Odd.
It's odd. It's got symmetry about the origin. So that's what you're going to write right here. It's odd. Okay. What'd you find about 7x plus 5? Why neither?
It's a straight.
It's a straight line that doesn't pass through the origin, so if you rotate it, it's not the same exact graph. If you rotate it half a turn, it's not the same exact graph. So what are you saying here? It's neither odd nor is it even. How you guys feeling about that? You understand the rules of symmetry regarding graphs? If I say, here's a graph of a polynomial, can you tell me if it's odd or even? Give me a thumbs up.
Yes, sir.
Awesome, very good guys, let's move. Next page, oh I love this stuff, this is so fun. Finding vertical and horizontal asymptotes, okay? Vertical and horizontal asymptotes. You guys want me to give you the cheat stuff to this?
Yes.
Okay. You could graph this, but there's an even easier way to do this, okay?
Well, looking at it.
Horizontal asymptotes, let's make a rule for horizontal asymptotes, I'm gonna call it ha over here. And rules for vertical asymptotes. Let's do the vertical asymptotes here, kids. You're going to have vertical asymptotes when denominator is what? Is what?
0.
Any vertical asymptote for this function?
0.
Okay. Any vertical asymptotes on this one?
3.
Anything else?
No.
Okay, let's just talk about the vertical asymptotes. Guys, vertical asymptotes come about when they make your denominator what value? 0. Okay. Does 0, when I plug 0 in right here, does 2 times 0 make 0? In the first function. Okay. How about this one right here? When I plug 3 in, 3 squared minus 9 makes 0? Negative 3 squared minus 9 makes 0? Does, right? So do you understand all the you understand all the vertical asymptotes in those two rational functions? First question. Okay? Now, horizontal asymptotes, there's kind of 3 rules. Okay? I'm going to write it this way. You always look at the leading degree of stuff here for horizontal asymptotes. There's like one rule. There's really 3 rules for horizontal asymptotes. I'm going to put them all here. 1, 2, 3. If you have a small degree over a bigger degree, and I should write up here, horizontal asymptote, look at degrees. If you ever have a smaller degree of a function over a bigger degree of a function, then your horizontal asymptote will always go to 0. What's the other possibility, kids? If you ever have a bigger degree over a smaller degree, it's either going to go to plus or minus infinity. And I'll show you why here in a second. But what if one isn't bigger than the other or one isn't smaller than the other? And what's that imply about the degrees?
Equal.
You got an equal degree over an equal degree. In that case, I'll tell you, I'm just going to say the rule would be divide and see what you get. Okay? So let's just talk about this. I'm giving you some shortcuts to this here, and I'll show you why. Horizontal asymptotes are tough for kids. Horizontal asymptotes are tough for kids because you're looking at end behaviors of the graph. Where is the graph going? Or what is the graph approaching in the very end? I've given you 3 rules up here. It says if you have a smaller degree over a bigger degree, where's it going? 0. If you have a bigger degree over it's either going to positive infinity or negative infinity. And if you have an equal degree over an equal degree, it says to do what? Okay, let's talk about this. Okay, look at my functions. 4 minus x squared over what? Okay. All you're concerned about is the part that has the highest degree. What's the highest degree up top? What's the degree down here? 1, right? So this says you've got a bigger degree over a what? So that means that this function, your end behavior, you might, oh, wait a minute. If I say horizontal asymptotes and they approach plus and minus infinity, are they really approaching a line or are they just going on forever? So hang on a second, kids. Here's the deal. What you would do is look at this x squared. This is bigger than this power down here. This is saying you have horizontal asymptotes at plus or minus infinity, but that just means it keeps getting bigger and bigger and bigger. So if it goes plus or minus infinity like this, guess what it means about horizontal asymptotes? There are none, okay? Now, I'm going to throw this into decimals here quickly. And I'm going to show you if this is true. Okay, somebody read that function to me. What over what? Let me clear that out of there. Okay, what's up top, kids? Is it 4 minus x squared? Divided by what? Ah, shoot. Was it divided by 2x? Guys, talk to me about end behaviors. As I go on this way forever, is there a horizontal asymptote? Okay, as I go all the way to the left, is there a horizontal asymptote? Okay, this is going to keep growing and growing and growing this way. This is going to grow this way. That's going down that way. It's going that way. Now, there's a line in here that is an asymptote. Anybody know what that line would be, by the way?
Negative x.
How about negative half x?
Yeah.
Can I try that? That's pretty impressive, Maddie. Okay. Do I know how I got that? The highest degree up here is just the negative x squared part, and this is just 2x. So you take the degrees that are highest in each and divide it out. So this x would take an x out there. You need to have negative half x. Now, guys, is that a horizontal asymptote or something else completely? Something else completely. So here's the situation I'm going back to. When they ask you about horizontal and vertical asymptotes, if you have a bigger one over a smaller one, what's that mean about horizontal asymptotes? A bigger degree over a smaller degree means you're going to positive or negative infinity. It means horizontally there are no asymptotes, okay? Talk to me about this over here, though. Well, I should write this down, I guess, first. Duh, Carson. There are none. Horizontal asymptotes, there are none. Okay, but what about horizontal asymptotes over here? Oh boy! What degree is the top? And what degree is the bottom? The degrees are actually what? So it says to do what? You only divide the parts with the highest degrees. The rest just become kind of nothing. They just go away. So in this case, what's 1x squared divided by 1x squared going to make?
1.
So you're going to have a horizontal asymptote at y equals 1. That's pretty simple, isn't it?
Plus or minus 1?
Well, it's just going to be 1 because the leading coefficient up here is positive 1 and the leading coefficient up there is positive 1. The x squareds would cancel, right, for any value of x. So you really have 1 over 1 there, right? What if you had 4x squared over 2x squared? Let's just check. Let's see if we do get a horizontal at 1. You guys are going to help me. I don't remember. Okay, what was up top? X plus 4? Divided by what? Whoa. asymptotes can be what? Let's put this horizontal in here, y equals 1, and see what we get. Okay? Do you agree with this? Oh boy. Did that horizontal get crossed?
Yeah.
But keep in mind, horizontal asymptotes come about when we look at end behavior. So I'm looking at really big numbers. Positive infinity to the right, negative infinity to the left. Let's zoom out a little bit. Is this flattening out? That line right there? Is this coming down across and flattening out right there? Do you see where the horizontal asymptote lies? You good with that, kids? Okay, remember, horizontals can be what?
Cross.
Okay, what do we say our verticals were there?
I'm
X
okay
equal
with
3,
that.
is that right?
And negative 3.
And X equal negative 3?
Yep.
So look like we've got it pretty well. Would you agree with that?
I don't like how they can be crossed.
The horizontals being crossed is kind of frustrating, isn't it? Okay?
Somebody's like, you can't just go on Desmos and look at it.
Well, you gotta be careful on all this, and there's reasons why, but I'm not too worried about the reasons why yet, okay? Alright, so let's talk here then. I wanna back up. Does this help you understand what horizontal asymptotes should look like, these 3 rules? Little shortcut for you, alright? So let's move on. It says write a possible function for the given graphs, okay? First of all, what degree does this appear to be?
3.
Easiest way to do this is as follows. Look at your x-intercepts. What are your x-intercepts?
Negative 2, 3.
So the way you would set this up, guys, you would just set this up as y equals some constant k times, here we go, x plus 2. Now the reason I'm putting x plus 2 in here, kids, is this. What value would go into x plus 2 first to make that 0? So when x is negative 2 here, y is what value?
Yeah.
So if I plug negative 2 in here, I don't care what k is. If I plug negative 2 in here, we're going to get out what for your y value? Okay. What do you think the next part of this is going to be given 3 as a, and then next what? Now the real kicker in this is the following. I plotted points that are where, kids? On the x-axis, right? So I'm going to try and zoom this up to be able to even read what I have over there. Okay, up there it says y equals blah, blah, blah. Enter fractions as what? Accurate to 2 places. The 3 roots should be entered in increasing order. So we write x minus 2 like this. X plus, we had a plus 3, right? And x plus 5. Didn't we? Or no, I've got that wrong. We had x plus 2, didn't we? Well, they want you to put negative 2 in here, that's why that's a plus, and then you put a 3 and then a 5 in here. Okay? Now, what other point did they give you? This here states that when x is what value?
0.
When x is 0, y is?
7.
Okay, so what we can do here, kids, is plug this point in. The second thing we choose to do is to come down here and say, let's plug a point in that's not on which axis down here?
So when all of that equals 0, y equals 7, so that means k equals 7, right?
Well, we'll see. We're going to plug it in. We're going to plug
No,
0 in for x, and we're going to plug 7 in for what now? So let's do that over here, okay? This is a point not on the x-axis, right, kids?
Mm-hmm.
So here we go. We're going to plug 7 in for y. That's going to equal k times, all right, what's going in for x given this point that we're using not on the x-axis? So what's 0 plus 2?
I done messed up. Never mind.
What's 0 minus 3? What is 0 minus 5?
Oh snap, k is going to be equal to, oh, awesome.
So from this, you've got 7 is equal to what? this times this times this would be
30.
over what?
Okay.
30 times what? Meaning k is what value? 7 over what?
30.
Okay. So my function becomes y equals, what do you want to put out front here for a k value?
7 over 30.
And this is really x plus 2, x minus 3, and x minus 5. I would encourage you, once you have that equation, to probably do what? Check it. Throw it into decimals. See if it matches what the graph is, okay? So let's have you guys try one together. See what you can come up with over here. We're going to talk a little bit more about double and triple roots, but how many roots are in this one? Okay. And then do you know a point that's not on the x-axis? You guys see if you can't write an equation for that function. Polynomial equation for that function. How do you want to start this one, kids?
Start by writing out everything. So y equals k, and then x equals 2, and then x minus 4, and then x minus 5.
How many agree? And what point did you choose not on the x-axis then?
0, 10.
So I've got 10 equals k times, here we go, 0 plus 2 would be what?
I'll do 1/4. Value equals 40.
Right?
Right.
So you've got 10 equals 40k.
Yep. So 10 over 40, which simplifies to 1/4.
So how many of you guys have y equals 1/4 times x plus 2 times x minus 4? Are we good with that, kids? That's an x minus 5 right there. How many had that? Okay. You okay? Oh no. You know what happens when you get older? More will fall out. Yeah. Kinda like mine.
My sandwich weighed 4/10 today.
Did it?
They made me smile.
I'm gonna try and get through this last example here on number 6 here. I think example 7. This ought to give you a really good chance to start your assignment and get you in some good shape. I really like this example, okay? I need a volunteer to read this here. This is gonna be a great example of, everything we looked at was rational functions up there. This is gonna be a great example of, everything at the top was polynomial. This is gonna be a great example of rationals here. Volunteer to read it?
After running 4 miles at a speed of x miles per hour, a man walked 4 miles that was 40 miles per hour slower. Express the time of the trip as a function of x. What horizontal and vertical asymptotes exist?
Okay, so I need to write this as 2 miles per hour slower. Okay, so make sure you get a 2 in out there. We're writing a function for what? You agree, time? Express the time as a function of x. Okay, help me out, kids. In science class, a rate is equal to a what? Isn't a rate equal to a distance divided by a time? So when I say I drive the rate of 55 miles, a distance per hour, a time, how would I write a formula then for time then? In other words, how would you get t alone here?
Oh goodness, this is bringing it back.
So I'm going to multiply both sides by t, right? R times t is equal to what? So what's your time t going to equal according to all of this formula stuff? So do you guys agree that we know from this right here, time is going to equal some distance over a rate? Would you guys agree with that? Now I gotta tell you in this problem right here, the man spent time doing what first? He was running.
I was running.
I was running. And I just kept on going. And I got to one side. I turned around, went the other way. We should watch that movie, shouldn't we?
Yes.
And then after that, he started doing what?
We should calculate how fast he was running in the driveway.
Yes, we should. He was booking it, wasn't he? You guys agree that he spent some time running and walking together? Okay. Let's talk about our time relative to this distance and his rate. Okay? It said a man after running how many miles first? And what was his speed? So his running time, t, I'm going to write this out. T, go back. Your time t would equal, let's do the running part first, would be how many miles did he run? What was the distance?
4
At a speed of what? So a distance 4 over a rate of x, that 4 over x is going to represent his time spent doing what, kids? Running. And then he walked how many miles?
4 miles.
Why x minus 2? It was 2 miles slower than the speed you ran, okay? So kids, I have a question. It says, what horizontal and vertical asymptotes might exist? Well, check this out. We know this. Vertical asymptotes occur when anything makes a denominator 0. So what's going to happen here? You can't run 0 miles per hour, can you? We know he wasn't running 0 miles per hour. We also know x can't equal what? X cannot equal 2 because if he was running 2 miles per hour, how fast was he walking? 0 miles per hour, which makes absolutely no sense, okay? So we know we've got vertical asymptotes where, kids? Okay. Now, let's go back to this idea of horizontal asymptotes, okay?
They can be crossed.
They can be crossed, but here's the deal. Horizontal asymptotes, go back to your rules up top here.
So they're equal. So we have to divide
What
it
is
out.
true? Do I have a smaller degree over bigger degree, equal degrees, or bigger degrees over smaller degrees? Is there any variable up top?
Smaller over bigger.
You've got smaller over what?
Touche. Bigger.
Bigger. So we're going to have, we're running a certain speed, and think about this realistically. I don't care how fast you go. Can you do something in 0 seconds? Can you get somewhere in 0 seconds?
Watch me.
It's impossible, okay? Because time is measurable, and it's a different time. You can't be in 2 spots at the same time, right? So where's your horizontal asymptote at, kids? Can't be at 0, okay? Because, and here it is, smaller degree over bigger degree means you're going to have a horizontal asymptote at what?
If
Okay.
Hermione Granger can do it, I can do it.
Okay. I'm going to stop there. Kids, I need to touch on